Welcome to this explainer. Today, we've got a highly focused, absolutely crucial topic on deck. We're going to teach you about the architecture of clinical psychology, specifically the research designs that act as the ultimate safeguard against our own human biases and professional hunches in therapy. Because if you've ever wondered how we actually know a therapy works, instead of just kind of crossing our fingers and hoping it does, well, you are in the right place. These designs are the essential frameworks that let us ask clinically meaningful questions and actually get objective, reliable answers back.
Here's our roadmap for today. We'll start with 1, beyond professional hunches, 2, between group designs, 3, within group designs, 4, threats and controls, and finally, 5, real-world applications. Basically, we're going to gently guide you from basic theory all the way to complex application without overwhelming you.
So, Section 1, Beyond Professional Hunches. This establishes exactly why we need disciplined thinking in clinical psychology. Before we can look at the how of research designs, we really need to nail down the why.
So the crucial point is that human beings, yes, even highly trained psychologists, are inherently biased. It's just human nature, right? We naturally notice things that confirm what we already believe and kind of ignore what doesn't. That is exactly why research designs act as absolute safeguards against those biases. They literally force disciplined thinking. By structuring exactly how we gather data, these frameworks allow psychologists to accurately weigh evidence and mathematically rule out alternative explanations rather than just relying on intuition or a professional hunch. We teach these methods because they're what ensure we deliver the absolute best services science has to offer.
And that brings us to this fascinating core tension we teach in psychology. On one side, you've got the nomothetic approach. Psychology, as a broad science, seeks to understand general rules and relationships among variables across massive crowds of people. But on the other side, clinical work is idiographic. It's entirely about applying those broad rules to understand the very unique, highly complex individual sitting right across from you in the therapy room. A great research design actually bridges that gap. It gives us general evidence that we can then confidently apply to our unique clients.
All right, moving on to Section 2, Between Group Research Designs. This is our first major methodological pillar, where we start comparing different groups of people.
The defining structure of a between-group design, which you might also hear called an independent groups design, is discrete comparison. We manipulate an independent variable, like a specific type of therapy. One discrete group, the experimental group, gets that intervention. The other, separate group, the control group, gets no treatment at all, or maybe they just sit on a wait list. By comparing how these two completely separate groups do before and after the intervention, we can isolate the actual specific effect of the treatment itself.
Okay, let's dive into this, because this concept right here is the absolute cornerstone of between-group research: randomization. When we assign participants to either the experimental or the control group, we do it completely at random. Why? Well, because people are different. They have unmeasured individual differences, stuff researchers call nuisance variables. Maybe someone just naturally exercises a lot more, or they have a rock-solid support system at home. By randomly assigning people, we make sure those nuisance variables are evenly balanced across both groups. It makes the groups truly comparable before we even touch the treatment manipulation.
Now, researchers have come up with a bunch of variations of this approach to answer very specific questions. You've definitely heard of randomized controlled trials, or RCTs, those tightly controlled true experiments. But I really want to highlight the dismantling design. This is absolutely brilliant when you have a complex treatment package and you want to figure out which specific part is doing the heavy lifting. Like, a researcher might use a dismantling design to test if behavioral activation all by itself is just as effective as the full cognitive behavioral therapy package for treating depression. We also use the constructive strategy, where we test adding new components to improve established treatments, and matched groups designs, where we purposely make sure groups are equivalent on specific traits, like education level.
Up next, Section 3, Within Group Research Designs. Here, we totally flip the script. In these designs, participants actually serve as their own control.
To truly grasp how this works, let's walk through the single-case A-B reversal design step by step. We track a single subject. Step 1, we observe their normal behavior. That's baseline A. Step 2, we introduce the treatment, intervention B, and watch to see if the behavior improves. Step 3, we actually withdraw the intervention, taking them back to baseline A. And finally, Step 4, we reintroduce intervention B.
Now, if the client's behavior changes precisely in coincidence with these transitions, like it improves, worsens, then improves again, man, that provides incredibly strong, almost undeniable evidence that the treatment itself is causing the effect.
But wait, you might be thinking, what if you're teaching someone a brand new skill? You can't exactly withdraw a learned behavior, right? You can't unteach someone a coping mechanism just to satisfy an ABAB design, and that is exactly where multiple baseline designs come in. Instead of withdrawing the treatment, we intervene across different behaviors or even different individuals after varying lengths of baseline observation. This totally solves the irreversibility problem while still proving our treatment works across multiple contexts.
And this brilliantly illustrates the strategic choices researchers have to make all the time. Between group designs, they're the gold standard for efficacy, and they completely avoid carryover effects since a participant only gets one treatment. But they require massive sample sizes. Within group designs, on the flip side, require far fewer participants, which makes them perfect for studying rare disorders, and they give us increased statistical power because individual differences stay constant. However, they're highly vulnerable to order effects, practice effects from taking tests over and over, and carryover risks where one phase just bleeds right into the next. Moving on to Section 4. Threats and statistical controls. Let's look at how researchers defend their findings and really stress test these designs against common errors.
When we run a study, we are desperate for internal validity, meaning we want to be 100% confident our treatment caused the change and nothing else. But we face some common enemies here. History refers to external, real-world events altering the results. Maturation means normal, everyday developmental changes could be responsible for the shift rather than our therapy. Then there's regression to the mean, which is just a fancy way of saying that extreme scores naturally tend to become a lot less extreme when you retest them, regardless of what intervention you use. And lastly, selection bias. This happens if there are systematic differences in how people are recruited or assigned to groups in the first place.
So how do we neutralize these threats? Well, we use some very specific primary control methods. To fight off those order effects and within group designs, we use counterbalancing, basically just varying the order the treatments are administered. To fight bias, we use blinding. This means we bring in objective raters who have absolutely zero idea which treatment condition a participant received. By keeping those raters totally in the dark, we guarantee a purely objective assessment of the client's actual progress.
Once we've controlled for all those threats, we've got to evaluate the data. We use statistical tools, things like t-tests and ANOVAs, to mathematically compare group means or analyze change over time. We also standardize our metrics into effect sizes, like Cohen's d. This essentially gives us a common mathematical language so we can combine results from tons of different studies into massive meta-analyses. But here is what I really want to emphasize. Clinical significance goes way beyond the math. Statistical significance just tells us a change happened. Clinical significance, though, that evaluates if the intervention actually moved the client into a normal range of daily functioning. At the end of the day, did it actually help them live a better life? And that brings us to Section 5, Real-World Clinical Applications. It's time to step out of the laboratory, walk into the clinic, and explore how these research building blocks actually change lives in the real world.
All of this rigorous therapy outcome research we teach is designed to identify empirically supported treatments, or ESTs, basically the therapies actually proven to work. A phenomenal example of this in action is the large-scale NIMH-TD-CRP study. Researchers use these exact methodologies to compare cognitive behavioral therapy, interpersonal psychotherapy, and medication for treating depression. By sticking to really strict research designs, they provided the clinical world with rock-solid objective data on which treatments work best.
But as we evaluate these applications, we have to make a super clear distinction between two vital concepts: efficacy and effectiveness. Efficacy is all about internal validity. Did the treatment cause the change in a highly controlled, perfect laboratory setting? Effectiveness, on the other hand, is all about external validity. Does this treatment actually work in messy, real-world settings with typical patients and everyday therapists? Because a treatment might have incredibly high efficacy in a pristine lab, but totally low effectiveness in a busy community clinic.
Now, what's really interesting about this slide is that as we bring these therapies into the real world, we absolutely must confront a critical gap: multicultural considerations. Historically, traditional research designs in those highly controlled efficacy studies often lacked diverse representation. This means an empirically supported treatment might not automatically translate to every single demographic. Because of that, evidence-based practice requires psychologists to thoughtfully adapt these scientifically validated interventions. We have to account for a client's unique culture, context, and values, ensuring effectiveness for everyone, not just a select few.
As we wrap up this explainer, I want to leave you with a crucial question to chew on. Which design will best advance our clinical knowledge today? You see, choosing the right design entirely depends on our current state of knowledge. If a field is brand new, case studies might actually be the best route. If it's a super well-developed domain, we need those strict randomized controlled trials. I really hope this structure empowers you the next time you read a psychological study, helping you look past the flashy headlines to analyze the framework itself. Thanks for joining me, and keep questioning how we know what we know.